This is Honors Algebra 2 Pre-Calc, Section 6.3, Pre-Calculus. We're doing example 13, which is a word problem involving vectors. Captain Marvel is flying at a speed of 50 miles per hour at a bearing of 20 degrees. At a certain point, she is hit by a gust of wind blowing due east at a speed of 15 miles per hour. Write the resultant vector in component form. What is her resulting speed? What is her resulting direction? Okay, so let's draw a picture of the situation, and I'm going to inch over here where I've got some space. Okay, so here's what's happening. If you're told a bearing, and we did this in probably section 6.2, if you're told a bearing without a direction, we mean north turn to the east. So a bearing of 20 degrees means, and if it helps you do the never eat slimy worms or whatever you say, sour watermelon, soggy waffles, whatever, right? So here's what we know. We know that she is flying north 20 degrees to the east, okay? So this is my Captain Marvel, and I'm going to use M as her vector, okay? So that's what she's flying, and that makes this 20 degrees, right? So this is 20 degrees, and it's a little hard to read, I apologize. Okay, when she's, at some point in her travel, she is hit by a gust of wind. So at the head of this vector, because we always add head to tail, right? She's hit by a gust of wind that is going due east, which is this direction. So this is my next vector, and I'm going to call that W for wind. So we have M for Marvel, W for wind. We want to know what's the resultant vector, right? So this is the resultant vector. I'm going to call it R for the result, okay? So what I want you to notice is that what's happening here is we're actually doing vector M, Captain Marvel, right? So we're doing vector M plus vector W should give me my resultant vector. So if I can write both M and W in component form, I should be able to add them pretty easily. So W is pretty straightforward in component form. W is literally no up and down motion and 15 miles per hour to the east. So W in component form is 15, 0, right? M in component form is going to be a little bit harder, right? M in component form, I'm going to have to look at that angle from the positive x-axis, which is a 70, right? So if I want M in component form, I know she's flying 50 miles per hour, right? So my M in component form is going to be 50, and then I'm going to use cosine of 70, comma sine of 70. And again, I know I'm a little bit out of space there, but you get the idea. So to write that M, and actually I can probably buy myself that space right here, M is going to be 50, and then cosine of 70, not the 20, sine of 70. Yeah, that's a lot more space. That was definitely better. So we'll erase all this nonsense. Okay, so essentially that's what my M vector is going to be, right? That's my M vector. So it seems to me that my resultant vector then, and I'm going to squeeze that down here and we'll make it work, is going to be 50 cosine 70 plus a 15, so 50 cosine of the 70 degrees plus the 15, comma, 50 sine 70, because the wind didn't change her north direction at all, right? It didn't change her north-south direction at all. So I'm going to put those in my calculator and get values. So 50 cosine of 70 plus a 15, and do make sure you're in degree mode, right? So I get 32.101, right? So the resultant vector is approximately a 32.101, and I'm actually just going to go ahead and store that as A in case I need it, because I'm going to need it. So I'm just going to let you know that when you're using something that you're going to need later, I'm going to store that as alpha A, all right? And then the second one is just going to be 50 sine 70, so I'm going to type in 50 sine of 70. I'm going to get that answer, which is the 46.984 or 85, and I'm going to store that as alpha B. Anytime you have to reuse something, it's a good idea to store it in your calculator so that you can reuse it later, and it's a great idea to write down what you stored it at so that you don't accidentally forget and not use the right thing. So I stored that as B. Okay, so that's my answer to part A, right? This is my answer to part A, but I'm going to use that answer to part A, right, to answer the other stuff. So I'm going to erase and give myself a little bit of space at the top, right? So part B said, what is her resulting speed? Well, her resulting speed, in the notation I'm using, my part B, is going to be the magnitude of the resultant vector, which I called R. So that's going to be the square root of the thing I called A squared plus the thing I called B squared. And because I stored them in my calculator, I don't have to worry about it not coming out exact. So I'm going to do the square root of alpha A, quantity squared, plus alpha B, quantity squared, inside those parentheses, right? So I hit enter, and I get that she's moving pretty fast. She's moving at a speed of about 56.902 3, or 4 miles per hour, which is not slow, right? It does make sense that the wind sped her up, right? Because she's not going against the wind is actually pushing in the direction she's going, right? If she'd been flying against the wind, it would slow her down, but notice that she was already going east, and then the wind went more east, right? And then what is her resulting direction? Well, that's going to be my theta, right? So C is going to be theta is the tangent inverse of the thing I called B over the thing I called A, because literally I called them A and B, which was very convenient. So I'm going to do inverse tangent. Notice I'm in quadrant 1, so there's no clever shenanigans to find the value, because in quadrant 1, it'll be pretty straightforward, right? So I do inverse tangent of alpha B divided by alpha A, and I get an answer in quadrant 1, which is a 55.658 degrees, approximately. Now, if you wanted to say as a bearing, so there's a couple ways you can say this. You could say east 55.658 degrees north, because you're facing east and turning this way from the positive x-axis, and that's fine, right? The other way you could say it, so you could say bearing of, right, this. You could find the other part. You could just find the missing part up here, up to 90, and you could say, cool, I'm just going to subtract that from 90 and get a 34. So you could just say a bearing of 34.341 or 2 degrees. If you don't specify a direction, you mean north turn to the east, okay? So, or you could have said it as north 34.341 or 2 degrees east, right? Any of those would have been okay, all right? So again, what it boiled down to here was writing each individual vector as component form, adding the components, and then doing my stuff to find speed and direction.